I'm sorry, folks. The last video ended promptly. I do only videos in 15-minute segments, which I think is important for students as far as kind of chunking the material. And I had not realized I was running over time. So we ended on the uses of isotopes. So isotopes are important, but they are radioactive, which can be helpful for measuring dating fossils and things that we find. Radioactive carbon-14 decays to nitrogen, so we can measure the amount of nitrogen that is available. Now, we use them often in today's world as tracers, and they usually help us to diagnose or visualize things like cancer. So one way to kind of look at this process is when we do some type of imagery in the healthcare field, sometimes we drink or take or we're injected with some type of radiation. It's usually a very low level, but what it does is it actually will flag certain areas of the body depending on where it's flowing to or where it's dispersed, how it's dispersed into the body. And then we can use imagery to actually see things. And this is important. For example, here, these are obviously the lungs that we can see, and we're looking kind of at a chest X-ray, but what we're actually seeing is the vessels within the lungs, which is actually really cool to see because of the radioactive isotopes that were added. Another place that radiation is actually used is on your berries that you buy in the store. So here's just a sampling of berries. If you buy things from the grocery store and they will be considered conventional, they usually have been sprayed with some type of radiation on the surface. The radiation helps to kill the bacteria on the surface of the fruit, helping them last longer and not creating a bacterial growth in which they will go rotten and bad very soon. So that's something to think about, and that's definitely some reason why you definitely should wash your fruit. However, I'm not sure that washing with just water will remove any radiation off the surface of your berries. So what's really important in chemistry, talking about our atoms, are those electrons. Now remember, we said the electron shells excuse me, are little kind of orbits around the nucleus. And so therefore, the farther away the electrons are, the more energy they have, potential energy that is, to do something with another atom. Excuse me. So atoms normally, again, have equal numbers of electrons and protons, and so therefore their opposite charges to kind of balance out, and an atom is what we consider neutral. So by itself, an atom is neutral. Now, electrons are attached to the positive nucleus, but remember, they're kind of revolving around that nucleus in these kind of orbital shells, and they can kind of be pushed to higher orbital shells with energy, and when they release their energy, they kind of fall back to one of the lower stated orbitals. We have this rule that we call the octet rule of distribution of electrons, and we usually use what's called the Bohr's model, which I'll show you in a moment, to show how the electron shells as circles are kind of around the nucleus. Now, each shell has 2 or more electron orbitals. So the innermost shell, which is the closest to the nucleus, always only has a maximum of 2. Okay, so our first kind of orbital can only have a maximum of 2 electrons in it. And then their others can have 8 or multiples of 8. Okay, now atoms that have fewer than 8 electrons in those kind of outer shells are usually chemically reactive, is what we call them. So if there's 3 or less, there's tendency for that particular atom to donate its electrons to another atom. But if there's 5 or more electrons in that outer shell, it has a tendency to receive more electrons from another atom. So it really kind of depends on what's happening in that extra shell. Excuse me. So here are our Bohr model examples. So in the center, which is what we would consider our nucleus, we have our actual symbol of the atom. So we know what we're talking about. Here's our first electron shell. Okay, so here's our first shell. And if you notice, there's 1, 2 electrons. And so that electron shell is full because again, the maximum amount in that first shell is 2. However, so if there are more electrons still, specifically in this atom, then we go to the next shell. And as you can see, the maximum here would actually be 8. And if that shell actually fills and we still have more electrons, then it's going to move to a third shell. And as you can see in the third shell, there is a pair, 1, 2. So how many electrons are in this whole entire atom? Well, if we counted them up, it's 2 plus 8 is 10 plus 2 more is 12. So there are 12 electrons. So how many protons are inside this wonderful atom in the nucleus? Well, there should be 12. So on and so forth. So you can see that each one of these is different. And again, depending on where they fall in the periodic table of elements will help tell us how many electrons there are. Here's lithium, for example. Here's 2 in our first shell, and it has 1 more, so it needs to kind of open up to this other shell. Now, would this guy be more willing to donate or accept electrons? Well, because there are less than 3 in that outer shell, there's only 1, it's more likely that this little guy is going to donate his electrons to another atom. Excuse me. So this sodium has 1, more likely to donate. This has 2, more likely to donate. This has 3. So it really might depend on the scenario, whether it donates or it accepts. But here, this is our wonderful carbon. Carbon has 2 in our first shell and 4 in the outside shell. This is more likely to be a receiver then, because there are 4. So it's more likely to receive electrons from another atom. And when we're talking about this kind of receiving and donating, we're talking about how atoms can bond together chemically. So bonds occur between atoms that are mostly caused by the electrons in the outer shell. The process of making or breaking these kind of bonds is what we call a reaction. So the intensity of simple reactions can be predicted by the periodic table and basically how many electrons might be in our particular atoms. So when we start putting atoms together and making them bigger, when we have 2 or more atoms that kind of react together with a bond, this is what we call a molecule. So atoms of the same elements could be a molecule. So for example, here's oxygen, O2. That's actually a molecule because we have 2 oxygen atoms. Here, H2, N2, etc. We have more than 2 atoms bonded together. That's a molecule, and again, these might be the same element. However, they can also be different elements. And when the materials are formed here and they're different elements, we definitely refer to them as a compound. So here we have a mixture. We have a carbon and 2 oxygen. So there are 3 atoms altogether. That's carbon dioxide. Here's water, H2O, 3 elements altogether. Here, C6H12O6 will become very familiar as we move on in this class, and that is glucose. That is our most basic sugar. And you can see here that there are 24 different elements that are making up this particular molecule. So again, they're very different when they're put together with their different atoms. Now, there are some different types of bonds. We can have ionic bonds and we can have covalent bonds. Ionic bonds, what you need to know about ionic bonds is to remember is that they are exchanging electrons. So they're exchanging, they're giving or receiving. So that octet rule comes into play. So when the atom wants to have 8 electrons in its outer shell, it depends on whether it's going to donate or receive. So basically here we're looking at 2 elements, usually at the opposite sides of our periodic table of elements. So for example here, sodium chloride. So if we had our table of elements open and we had sodium chloride, so sodium is Na, chloride is Cl, okay? The sodium is way on the left side and chloride is way over on the right side, so they are very much so different. Now, this is what's really important is what's going on the outer shell. So in the outer electron shell, sodium has 1. Okay, so if it only has 1, is it more likely to donate or receive? More likely to donate. Chlorine, which we would say is sodium chloride when it kind of bonds together, is all the way on the right side, and its outer shell has 7. Now remember, the octet rule is to be in this kind of happy place, is that we want 8 electrons in the outer shell. So this little one is more likely to receive electrons. So what happens is when there is a reaction with these guys, they are exchanging, and they're giving and they're receiving. So that's what refers to it as an ionic bond. So basically sodium completely gives up its outer electron to the chlorine. And so what happens, because we exchanged that, the sodium is now more positive. Why? Because it gave away one of its electrons, and usually our electrons and our protons are equal, and so therefore when they're equal, we are neutral. But when it gave away its its electron, we have more protons now. So this little guy is going to be what we consider Na positive. Okay, and since our wonderful chlorine accepted one in, it has one more electron than it normally would. So there's one more electron than there are protons, and so it actually has a negative charge now. So because of this, they are opposites, and opposites like to attract and they like to bond to each other. So that is a true statement when we talk about chemistry. Now, NaCl is an ionic compound that we basically use in our everyday life as table salt. Again, if you buy salt in the store that's naturally occurring, or basically something that's made in a lab setting, you're using sodium chloride. So here's our table salt. Now here's some Bohr models, which I think is sometimes that visualization is really helpful. Here is the Na. There's 2. There's 8, and then there was one more right here. Okay, here is our chlorine. It has 2, it has 8, and then it had 7. So what's going to happen is this guy is going to basically hand over its electron to here. Now, is this one happy because it's got 8? It meets the octet rule. Its outer shell has 8. Now, if we kind of look back over here, is Na happy? Because honestly, we can kind of get rid of this outer shell now, and the inner shell has 8. And is it happy? Yes. So both of these have approved the octet rule, and they are significantly happier. And here's another, this is another way to look at it. This is like a dot diagram of just the outer shells and how, again, they would bulk off. So it would be Na plus Cl minus. Okay, and again, that's because we've exchanged our wonderful electrons. Now, the other type of bond is covalent. Covalent bonds, I will probably begin in the next video, but covalent bonds basically share electrons. So this is what's different. Covalent bonds usually are very close to each other on the periodic table. And basically they want to share and create a pair of electrons in that outer shell that they both make the octet rule, and therefore they're happy. So one atom gives usually one electron and the other atom gives another electron, and they share it together so they become stable. However, sometimes we can have triple covalent bonds and double covalent bonds where maybe there's 2 electron pairs shared or 3 electron pairs shared. That definitely can happen. But here's some examples, excuse me, of covalent bonds. This is our wonderful water. Water is polar. We'll talk about that more later. Here is CH4, which is actually methane. This is a nonpolar, but it's a covalent bond. And this is CO2, which is our oxygen, which actually has a double bond. That's what that 2 little lines with an equal sign means, is it's double bonded. This is a nonpolar covalent bond, which basically means each one of these is sharing an electron with another atom to make it happy in that octet setting and more stable. So, nonpolar covalent bonds are more common. They are basically 2 elements that are equidistant from the edges of the periodic table. They have an equal affinity for that electron. So one will want to donate and the other one will want to kind of receive, and the intensity is about the same. When they're bonded covalently, they spend an equal amount of time between both atoms. So they're equal opportunity, wonderful electrons. So such covalent bonds are considered polar. So, nonpolar. So that just means that they like to sit with their electrons shared equidistant, equally equally amongst the two atoms. Now, water is a polar covalent bond, and we're going to begin the next video talking about polar covalent bonds.